Okay, here we go. Scale models, lesson 4. Linear scale factors, surface area, and volume. So last video, we looked at the relationship between, and I'll just do it up here. Last video, we looked at the relationship between linear scale factor and area scale factor. And we found out and we noticed that if we could do one of two things. We could square our linear scale factor and it would be equal to our area scale factor, or we could square root our area scale factor and it would be equal to our linear scale factor. So depending on what we're given. Okay. So then I'm going to ask you the question, well, what's the difference between area and surface area? Pause for a little bit of effect, make you think a little bit. Really, the only difference is that if we're talking about area, we're talking about the space that a two-dimensional object fills. This is the area of this rectangle. As soon as I make that object three-dimensional, now I don't just have a rectangle, but I have a rectangular prism. I can't talk about area anymore. I can talk about area of one of the faces, but if I want to talk about the area of all of those faces together, the top, the bottom, the two sets of sides, then I have to refer to that as surface area. Okay, so the difference between area and surface area is the difference between a two-dimensional object and a three-dimensional object. Otherwise, nothing is different. So really, now we can say my linear scale factor, if I square it, it's equal to my area scale factor. If I take my linear scale factor and I square it, it's also equal to my surface area scale factor. And vice versa. I could square root my area scale factor, like we just said, and get my linear scale factor, or I could square root my surface area scale factor and get my linear scale factor. So this part doesn't change at all. We would see the exact same relationship between linear scale factor and surface area scale factor if we looked at area scale factor as well. It's the same relationship, squared. So just as a quick one, I'm only going to do a couple of examples through this because it gets very convoluted at some point and I tend to lose students, and I find it easier and they grasp it better if I keep it down to like simple. Okay, so if we look at, we'll look at the first two on this one. How's that? Our first figure is now a rectangular prism of some sort. It measures 3 by 5 by 1. My surface area, my original surface area. So if I'm looking at my figure, it's going to have 6 faces, 3 by 5 by 1 deep. Surface area is the surface area of this face times 2 because there's one on the back. It's this face times 2 because there's another one on the back, and it's this face times 2 because there's another one on the back, on the left side. Now to figure that out, the formula is a little bit more, not more complicated, but you have to go 3 times 5. That's one face, but there are 2 of them, times 2. And then I have to go 1 times 5. That's a plus, should be times, should actually be a 1. 1 times 5 times 2, because there's 2 of them. And then I have to go 3 times 1 times 2, because there's 2 of them, and add them all together. Plus. 3 times 5 times 2 is 15. 1 times 5 times 2 is 10. 3 times 1 times 2 is 6. 15 and 10 and 6. 10. Oh, wait a minute. Some math is not working out here. What's going on here? You should be saying bad math, Tommy Emma. 3 times 5 times 2 is not 15. 3 times 5 times 2 is 30. 30 plus 10 plus 6 gives us our 46. If I apply a linear scale factor of 2 to 1 or 2 to these dimensions, I get a new figure that measures 6 by 10 by 2. And then I go 6 times 10 times 2, and I go 10 times 2 times 6. No, sorry, times 2 because there's 2 of them. And then I would go 6 times 2, and then there's 2 of them. 60, 120 plus 40 plus 12, 24, 24, 184. And then I compare my new surface area to my old surface area. 184 to 46, 184 by 46. Both of these divide by 46. I'm guessing you could divide by 2 and 2 and 2 to get there. But you get down to 4 over 1 or just 4. And you can see that this scale factor for my surface area, I'll erase that, scale factor for my surface area is my linear scale factor squared. Okay, so that's the important relationship that you have to see. And you can see how convoluted some of these calculations get. And I tend to lose students when I try to go through them. So we're not going to go through them all. But we'll look at these. If this is my linear scale factor and my area scale factor is squared, this should be 1 over 36. I go 1 over 6 times 1 over 6. 1 over 36. If this is my linear scale factor, 3 over 2, I go 3 over 2 times 3 over 2, 9 over 4. If this is my linear scale factor, 2 over 3, I go 2 over 3 times 2 over 3 is 4 over 9. I could work that backwards. Let's say that my surface area scale factor is 16 over 25. I take the square root of 16, that gives me 4. The square root of 5 gives me 5. There's my linear scale factor. So I take the square root of 16 and 25. Okay. So just like the other lesson, surface area scale factor is equal to my linear scale factor. Let's get that nice and neat. Squared. Or I can take my linear scale factor and square root it to get my surface area scale factor. Okay, so that's the important relationship that you see. It's exactly the same as area scale factor. And then we have a quick look at volume. Volume scale factor. So here's our 3-dimensional figure. So here's our original rectangle. We can apply a linear scale factor. We can apply a linear scale factor. We can figure out an area scale factor. But now I need a 3-dimensional object. I can still apply a linear scale factor, but now I have to apply a surface area scale factor because there are multiple faces. And because of that, when I have my 3-dimensional object, how do I calculate the volume of that object? Length times width times height. And if all of these were in centimeters, then it would be centimeters cubed. So if I know that I go from linear scale factor to area scale factor by squaring, how come I going to go from linear scale factor to volume scale factor? Hopefully you think, well, maybe I just cube it. Well, let's have a look. Again, I'm only going to do the first one just to make sure that we can see it. Okay. Our original dimensions of our figure, 3 by 5 by 1, still gives us, it's the same figure as we started with before, except volume is length times width times height. 3 times 5 times 1 is 15. If I apply a 2-to-1 scale factor, linear scale factor to these dimensions, 3 by 5 by 1, I get 6 by 10 by 2. And my volume becomes 6 times 10 times 2, which is 60, which is 120. And then I look at the relationship between my new volume and my old volume, 120 to 15. which reduces down to 8 to 1. Now let's do that. If I divide this by 5 and divide this by 5, I get 3. This by 5, I get 24. And both 24 and 3 divide by 3. By 3, that gets me my 8 to 1, or just 8. And you can see that 8 in relation to 2 is 2 cubed. 2 times 2 times 2. So you cube it. Or you could work the other way around. You cube root it. So if my scale factor, linear scale factor was 5, my volume scale factor would be 5 cubed, or 5 times 5 times 5, or 125. If it's 1 over 6, then I'm going to go 1 over 6 times 1 over 6 times 1 over 6, which is going to give me 1 over 216. 3 over 2, I'm going to go 3 over 2 times 3 over 2 times 3 over 2. 3 times 3 times 3 is 27 over 2 times 2 times 2 is 8. Okay, so you cube it to find your volume scale factor. Volume scale factor is my linear scale factor cubed. And again, we can work that backwards. If I have my volume scale factor and I cube root it, I will get my linear scale factor. So it works both ways. And I think you get one of those questions. You get a question like that, in which you have to fill in a table. Okay. This process of using squares and cubes back and forth with these scale factors, it's called the square cube law. And the next couple of pages go over all of that, but you really, it gets far too complicated and too wordy. So you just need to understand that the square cube law is how we represent, or we talk about, the relationship between linear scale factor, area scale factor, surface area scale factor, perimeter scale factor, and volume scale factor. Okay, all kind of put together. And the best little piece of tidbit over on the next page is this one. Scale factor relationships. Perimeter scale factor is equal to linear scale factor. Area scale factor is equal to the linear scale factor squared. Or you could say that the square root of area scale factor equals linear scale factor. Surface area scale factor is equal to linear scale factor squared. Same thing. Or the square root of surface area scale factor is equal to linear scale factor. And volume. Volume scale factor is the linear scale factor cubed, multiplied by itself 3 times, or the cube root of volume scale factor is equal to linear scale factor. Okay, this is the best table to understand right here. The key out of section or lesson 1.4 or lesson 4 here. And I realized that putting that in red might not make it legible. So let's erase it. There. Over the page, skipping all of this, don't need to go over that. Talks about the square cube law, which I talked about. Well, how do we apply it? Can we see it? Let's look through this example. Example 1, Axis Globes Limited produces globes with diameter 30 centimeters. Isabel is the manager of Axis and has her employees construct a globe with a diameter of 1.5 meters to put on the roof of their building. Surface area and volume calculations of the globes with the diameter of 30 are shown below. Calculate to the nearest tenth of a unit the surface area and volume of a globe with a diameter of 1.5 meters. So that's our first step, do those calculations. Okay, so here we go. So they've already calculated the surface area and volume using the formulas, surface area and volume of a sphere for a diameter of 30. So you're probably wondering, well, this is 30, but this says 15. So remember, our formula uses radius. Radius is half of the diameter. So now I need to do this for the 1.5 meter globe. 1.5 meters is 150 centimeters. And half of that is 75. So 75 centimeters is my new radius. I put that in my formula, 4 pi r squared, or 4 times pi times 75 squared. I get 70,650. And I do the same for my volume. 4 over 3 pi r cubed. But 75 is my radius cubed. You should get 1,766,250, and we're talking centimeters cubed here, and these are centimeters squared. Areas, surface area or area squared, volume is always cubed. So for question A, they're just wanting you to get used to using some formula work and doing some math. Question B, determine the following. What's the linear scale factor? So remember, scale factor is always drawing over actual. We know our original is 30. Our enlargement is 1.5 meters or centimeters, of course, 150 centimeters, 30 centimeters. That reduces by doing division. That gives me 5. My linear scale factor is 5. My surface area scale factor, remember, is our linear scale factor squared, which is 5 squared, which is 25. My volume scale factor is my linear scale factor cubed, which is 5 cubed, which is 125. Easy way to determine those. First, figure out your linear scale factor, then you can square or cube. Illustrate how these represent the square cube law. Don't really need to do that. I won't ask you to do anything like that. You just need to understand how the square cube law works. Question D, show how to use the volume scale factor to determine linear scale factor. So now we know that our volume scale factor is 125. Remember, I told you to get from volume scale factor to linear scale factor, you cube root the volume scale factor. So I'm going to cube root 125, and that gives me 5. And you can work this thing all the way backwards and forwards. Question E, show how to use the volume scale factor to determine area scale factor. Well, I just used my volume scale factor to determine my linear scale factor of 5. Oops, I'll put LSF. How do I go from linear scale factor to area scale factor? I square it. 25. Okay. So really what could happen is you could be asked to determine a scale factor. Linear scale factor generally is what they refer to. We know that that is equal to perimeter scale factor. I know that I can go from linear scale factor to area scale factor, oops, by squaring. And I know I can go from linear scale factor to surface area scale factor by squaring. And I know that I can go from linear scale factor to volume surface area by squaring. So really, you should be able to do all kinds of different circles here. I should be able to go from linear scale factor to any of these. I should be able to go from surface area scale factor or I can go from area surface factor to linear scale factor, surface to linear, volume to linear, and then go from linear to area and back and forth and back and forth. So it's a whole bunch of overlapping like ellipses or circles. You should be able to do those calculations backwards and forwards. Okay. So some questions are going to get assigned, and because we're at the end of the unit, we'll probably have a hand-in assignment, and then a test will be coming shortly. See you next time.